Awesome. Thank you so much for allowing me to be here. This is a great meeting. I think CSO we got maybe a couple of years ago had a little bit of a brief presence, but I'm here with to sort of talk about a lot of the new developments that we have going on, and really happy to be spending the evening here. So thanks again. So I know a lot of times speakers sort of thank their colleagues at the end of the talk. I sort of like to do it right at the beginning because I don't want it to be like I'm taking the credit for all of this. So CSO is this huge team effort that's been going on for about 5 years now, and I'm just here representing that teamwork. I especially want to thank Nina Aragon, who is a Ph.D. student here at Oregon State. She's led a lot of the snowpack modeling work that you'll see here tonight. And then also we have this great sort of group of project ambassadors that are sort of all over the United States, and we've got a few internationally as well. And they're all, mountain guides, professional athletes, snow scientists, educators, and then just backcountry enthusiasts, people who like to be out in snow and tell us about it. So they all help to support, advertise, improve this project, and also to help educate the public about the project and snow and water in general. So basically, there's really three main topics I'd like to cover tonight. I'd like to briefly introduce what the Community Snow Observations Project is about and what role it plays in informing us about snow distribution. The second thing I'd like to do is to sort of briefly show some results that kind of demonstrate that this project is successful and that we are able to significantly improve models of snow distribution when we include, or what's called assimilate, snow depth measurements from CSO participants. And then finally, I want to sort of explain the operational side to what we do. And this is a bit newer. We only started this about 12 months ago. And we presently model about 15 domains across the United States, and we serve up near real-time, high-resolution grids of snow depth, changes in snow depth, and other sorts of snow information online. Okay, so we all have interest in snow for personal recreation reasons, of course, and many of us also for work reasons. We and the environment around us, we ask a lot of our snowpack. It stores snow in the winter months and it gradually releases it in the spring and summer. So snow functions as a natural reservoir, of course. It reduces peak flows in rivers. It helps sustain water availability in late spring and summer. Snow also provides habitat for a variety of species in the winter, and it also helps keep river temperatures cool throughout spring and early summer. Despite the importance of seasonal snow, the distribution of high mountain snowpacks is not as well known as we might like, especially in these high elevation complex terrain areas. And this is due to the challenges, of making measurements in these locations, and improving understanding of snow distribution in these areas is really the key reason why CSO was founded in the first place. So there are three primary ways in which we get information about snow distribution. We can directly measure the snow, we can remotely sense a number of properties of the snow, or we can use models to estimate properties of the snow in areas where we may not have measurements. So these are kind of the three legs of the stool of snow science. We typically are interested in snow depth, snow water equivalent, snow density, and certainly vertical structure of the snowpack as well. So remote measurements, I'll start there. Remote measurements are amazing. These can be made from fixed platforms like an instrument tower, or they can be made from a mobile platform like a plane or a satellite, or these days a drone. All right. And the general idea of it is, it's complicated in terms of expensive equipment and all that, but the general idea is really simple. It's just subtractive. So the distance between the measurement platform and the bare ground is taken to be a known quantity based upon direct measurements or high accuracy GPS information. The distance between the platform and the snow surface is then measured. And this is done by timing how long it takes a signal like ultrasonic sound waves or laser light to sort of go from the measurement device, bounce off the snow surface, and then come back to the instrument. So the difference between those two things then gives you the depth of the snowpack itself. That's all there is to it. Now, for a fixed platform, these measurements can be repeated continuously, and you end up with a time series of snow depth information at a single point. For a moving platform, if you sort of make measurements consecutively in time and then mosaic them together, you can get a really nice high density spatial map of snow depth. And so this is just one example. This is from some field work that I was involved with this spring up near Girdwood, Alaska. So these slide corridors, which you can obviously see here, are a hazard to both highway assets and then also a railroad, which passes right through this narrow corridor between the steep mountains and then the ocean inlet. So repeat LiDAR flights, say every month or so, are really useful for tracking slide path activity and other types of snow redistribution processes. ISAT-2 is a great example of satellite-based LiDAR. So this mission launched a few years ago. And just to point out, if you're interested, there's even an app that you can get on your phone so that you can see when the satellite is coming to your neighborhood. So I looked this up. This is kind of November 26th is the next time that it's going to be passing by, sort of where you all are in New Hampshire. Now, this has a revisit period of about 3 months, so it doesn't come by all that often. But ISAT data can be used to sense changes in things like lake levels, glacier ice thickness, and some people are looking at this as a way of measuring sort of seasonal change in snow depth as well. So measurement platforms can't be every place at every time. So remote measurements are a kind of a constant trade-off between things like spatial resolution, temporal resolution, and then also vertical accuracy of the measurement. So in situ depth measurements are pretty simple and they're very low tech by comparison. All right, you really just need to go out into the snow with a meter stick or an avalanche probe, something like that. Stick it in the snow in a few places, make sure you're not hitting a hole or a rock, something like that, average the results and you're done. If you're interested in the water equivalent, you can use a coring device such as the federal sampler to extract and weigh a column of snow. So this is an example of this type of work that we do up in Alaska often. This is definitely more difficult and time consuming than measuring snow depth with a probe, but it's still relatively low tech and it's still relatively low cost. The only limitations to these types of in situ measurement techniques are really your time, your effort, and I guess your fitness, and depending upon where you're trying to go and measure things. So a more automated way to measure what's called the snow water equivalent, or SWE, is by using snow pillows. Okay. Now, there are different kinds of snow pillows out there. Some are more exciting than the other. So the snow pillow on the right is not what I'm talking about here. The snow pillow on the left, this is what I'm talking about. It's not that complicated. It's really just a sort of a fluid-filled bladder that lays on the ground, and it's connected to instruments that measure pressure. So as the season goes on and the snowpack builds, the pressure in this bladder increases. So honestly, it's really just like a bathroom scale that's weighing the weight of the snowpack above it. Okay. So in the Western United States, we have amazing access to real-time in situ depth and SWE measurements. What are called snow telemetry sites are scattered around the Western United States. We have about 800 of them or so. They have varying periods of record, but many of them go back about 40 years. So this is a really nice, dense set of data for us to be looking at. Now, in addition to this, we also have what's called a snow course network, which is maintained by the same organization, the NRCS, as the snow telemetry network. Snow course sites, they have much longer periods of record. Some of them go back over 100 years. And these are sites where they make manual measurements, typically once a month, sometimes twice a month. Now, in the Eastern United States, the pickings are frankly quite a bit slimmer. There are not snow telemetry stations. There are a few what are called SCAN network stations, and that stands for Soil Climate Analysis Network. And there's one at Hubbard Brook, for example. So that's great, but there's just not as many, unfortunately. Now, these are federal data sources. In addition to these federal assets, many states do have their own snow survey programs, and many of the snow survey programs in the Eastern United States are amazing. So there's really good records of snow depth there. Many state departments of transportation also collect snow data, and then of course, the regional avalanche centers typically collect and distribute some amount of snow data to the public. So that's remote measurements, that's in situ measurements. Now, snow models, okay, these can help fill the gap in space and time between measurements that we might have. So what you're looking at here is an image of snow water equivalent, or SWE, on a particular day of the year. It doesn't really matter. And this is estimated by what is called the Snow Data Assimilation System, or SNODAS. Now, this is run by the National Operational Hydrologic Remote Sensing Center, which is a mouthful, but basically it operates under NOAA and the National Weather Service. So SNODAS products are available on a daily time step, which is great. They're available at a 1 kilometer spatial scale, which is not great. That's fairly rough, but they cover the entire United States, which is amazing. And so there are many different snow models available out there. This is one of them. And you can roughly categorize them as being what are called statistical models or conceptual models or physically based or process-based models. And then even within one of these single categories, there's all kinds of different sort of flavors of them. So there's really a lot to choose from in terms of our ability to try and estimate snow properties using computer models. So this sounds good. It sounds like there's a lot of information out there, and there is, but there are still gaps. You know, SNOTEL sites, which I mentioned, are fantastic because they're measuring stuff all the time. However, they tend to be, but as we saw, they don't cover half the country in the first place. And then also, even out west here, they tend to be in moderate elevation areas that are fairly gentle in terms of terrain and terrain complexity and slope. And the reason for that is because you need vehicular access to install and maintain these. The SNODAS estimates are also super cool in terms of great coverage, but they are fairly coarse spatially. And also, they have been shown to not do a great job in high mountain areas. They don't seem to get the snowpack quite right. So the Community Snow Observations, or the CSO project, was funded by NASA in 2017 with the initial goals of helping to fill these gaps by crowdsourcing snow depth data in complex mountain environments. Anybody can participate in this program for sure. It's really easy. We tend to prioritize participation by backcountry recreationists and snow professionals because these are the people that are kind of getting into these areas where we lack and really want snow information. Okay, so how does the sort of overall idea work? And this is just obviously a little cartoon sketch of it. And at the core of it, okay, at the core of what we do is a process-based snowpack model, right? That's the blue box. So this model is driven by a number of things: weather data, terrain information, land cover information. Those are all the purple inputs. Now we calibrate our model using the best available snow data, and this might be SNOTEL information. This could be snow core sites. This could be snow data that comes from a research project, these kinds of things. Once we've calibrated our model, we could just run it, right? Grab a cup of coffee, sit back, see what the model says. And it would give us estimates of snow properties. That's terrific, but models don't always get things right. And so where CSO comes in is basically this orange box and this red box. We bring into the modeling chain, or what we do is it's called assimilation. We assimilate in participant observations as they come to us throughout the snow season. So if we get a measurement and if it disagrees with the model prediction at that location and that time, we basically fix the model, we patch the model. And we do this over and over again throughout the snow season. Okay, so before I get into all the details of this, first of all, are there even enough backcountry participants out there to make a difference? You know, if you haven't been, the picture here on the left, this is Mount St. Helens, which 15 years ago was a nice quiet place to sort of backcountry ski. And this is sort of what we get at Mount St. Helens now on a typical nice spring weekend. There'll be 400 or 500 people up at the rim. So absolutely, there are plenty of people out there. And then the picture on the right, I'm sure everybody recognizes this. This is basically the Strava winter heat map. So people's phones are out and they're recording their tracks, and this is kind of showing you where people go in the wintertime. And again, plenty of people are out there in these complicated areas where we would like to get more snow information. Okay, so let's kind of go through things bit by bit, and I'll first talk about the model. There's a lot on this slide, and we don't need to worry about it all. I just want to have some of the key sort of citations here in terms of what we do. So we use a process-based snowpack model, largely authored by Liston and Elder, and we've made some changes to make it work for our own needs. We bring in weather data, and then this weather data gets sort of interpolated to a higher resolution model grid, and then we can run the snowpack model itself. Okay, and if you only care about the snow, you could basically stop here. If your interests are more in water resources, there are other things that we do. So we do things like evapotranspiration, soil moisture balances, and so on. And then the last box that you see at the lower right is a model that basically allows us to do the stream flow. So we start with the weather, we go through the snow, and we end up with water flowing over the landscape. We run these models at a variety of scales and resolutions. And what I mean by this is, if you think of a model grid as being a checkerboard, the sizes of the squares on our checkerboard are typically 25 to 50 meters in size. And we run the model and it spits out data on a daily basis. So participating in this project is easy, and that's by design. You really just need three things. You need to have an Avalanche probe or some other measurement device, which you should have with you if you're out in the backcountry anyway. You need to have your phone with you. And then finally, you need an app, right? So we actually started this project 5 years ago using what's called the Mountain Hub app. And actually, we acquired Mountain Hub from Mammut. They briefly owned it, and then they sold it to us. So we owned it for a couple of years. But we have just recently, and this is an important point, we have just recently transitioned to a different app. So we have a partnership now with Propagation Labs, and we are using what is called their Snowscope app. Some of the reasons for this is that the Snowscope app is unbelievably easy to use. It's like 3 taps on your phone and you've entered a snow depth and you're done. And we get that data to us. So that is the primary reason for the change, is that ease of use and the ability to very easily acquire data from it. I also want to point out that we get data from what's called the Snow Pilot project. Now, Snow Pilot, if you've not heard of that, it's a desktop application that is used by a lot of snow professionals like patrollers, and also avalanche forecasters and so forth. So you can either use Snowscope or you can use Snowpilot. One of those platforms, a phone and a probe, and you're all good to go. So this sequence of images, these are just some screen grabs from the Snowscope app. This is basically what you see when you go through submitting a data point. You touch the plus button to add a data point. You say that you'd like to add a snow depth. You tap in the snow depth. You hit save and you're done. It's that simple. The other things that you will see on this app is that there are ways of logging actually snow pits using this app, but we don't use that for the CSO project. We're just interested in the overall snowpack depth. Okay, so snow depth is great, and this is what we ask people to measure. But what we do in terms of modeling the snowpack, we actually have to assimilate in the snow water equivalent, okay, which is a different thing. Now, the relationship between snow depth, snow water equivalent, and the day of the water year is shown in that central figure where you see all the colors. So squeeze on the vertical axis, depth is on the horizontal axis. Essentially, the ratio between those two things gives you the density. And so early in the snow season, like from day 0 to 150 or so, the snow is colder, it's a little bit drier, so the snow density is lower. And then as we go through the rest of the snow season, getting into those yellow colors, the snow density gets higher. Okay, and the reason for that are processes like compaction, melting of the snowpack, and so forth. So part of what we have had to do is that we have had to come up with a sort of an improved model that allows us to very quickly go from a snow depth, which has been submitted to us, to a snow water equivalent. All right, and that's basically what I'm talking about here with the paper on the left. And this is a really quick and easy tool to use. It really just has to do with what day of the year is it, where are you in terms of the characteristics of your climate, and it'll give you a snow density. So it's a really easy thing to use. Okay, so now that we have taken our snow depth, we've turned them into snow water equivalent, and now we can start doing our modeling. We get all the time, we get questions from the people about, from the public about like, how do you know that the data that you guys get is any good? How do you know, what can you tell me about the quality of that data? That's a fantastic question. And there's many layers to the answer, I would say. With any community science project, you have to recognize that you are working with unpaid volunteers. These are not trained professionals. So we make things as simple as possible. We only ask people to measure snow depth. We don't ask them to measure water equivalent. We provide tutorials on our website about how to do it and things like that. The other thing that we do, though, is we do try to compare the measurements that we get to other sources of snow information out there. But the problem is there's not that many. The only one that really covers the whole country is the SNODAS model, which I mentioned earlier. There's a few problems with that. They're fairly coarse in scale. They're a 1 kilometer scale, and they do okay overall, but sometimes they really get the snow wrong. And so this picture that you're looking at on the left here, this is from the Tetons. And the image that you see is an image from the Sentinel-2 satellite. And so you see a whole bunch of snow still covering the main Teton range. And then the colored boxes that you see, these are the estimates of snow cover from SNODAS. And you can see SNODAS thinks that there's hardly any snow at all over that mountain range. So we have to be a little bit careful about comparing the observations that we get to the actual SNODAS estimates of snow on a given day. And so instead, what we do is we think about things from a statistical point of view. So if we get a CSO measurement, which is that red dot that you're seeing there, on a particular day of the year, what we do is we look at the entirety of the SNODAS record, which is like 20 years of snow information. And we look at the properties of the distribution of that snow information. So the envelope that you see on this figure, you see the thick blue line, and then you see like a lower line and upper line. This is kind of showing you at that location, the minimum, the average, and the maximum snow that SNODAS has ever estimated. So when we get a measurement, if our measurement is like way outside of those bounds, we might flag that as a point that we have to remove. So in this case, that red symbol that we got was within those bounds. So, we don't know it's perfect, but we tend to keep it because we don't have a reason for disqualifying it. And this figure here shows you a little bit of an example of how we apply this process. So all of the points that you see there, all of the dots there represent the CSO measurements that we got, let's say over 6 months of the project. We took all of those measurements and we kind of ran them through our quality assurance check. And then all of the yellow symbols that you see are symbols that were identified as being potentially suspect. And so we throw them out and we don't use them. And we just use the ones that seem like they're good enough for our purposes. So that's kind of how we handle sort of data quality assurance. So a cartoon example of what we do with these observations is right here. So this dark blue line, this is sort of showing you the snow water equivalent of the snowpack over a given snow season. We see the snow grow and then it goes away really quickly during the ablation season. Well, the red dot, you could think of that as being one single CSO observation that we got. Based on that observation, then our model output gets changed to try and make the model output actually go through that data point. And it's that simple. So this assimilation process is something that just is looking at the observations and then nudging the model towards those observations. Now, in practice, we would hope to have measurements like these red dots coming in like every week, every 2 weeks, every day, something like that, so that the model would sort of constantly get these refinements. Okay, so in most regional to national snow modeling efforts, observations from snow stations like SNOTEL are the primary source of data that gets assimilated in the snow models. Now, the problem with that, though, is in high mountain areas, we may not have very many. So this picture here is showing you the Big and Little Cottonwood Canyon east of Salt Lake City, right? And we see 4 SNOTEL sites in that picture. Those are the sort of the pink symbols that you're seeing. All of the blue symbols that you're seeing, these are the CSO observations that have come into us in this area. And so you can just sort of imagine that by having all of this information which is distributed across the landscape, it's going to help us a lot in terms of making our estimates of snow distribution over that landscape a lot better. The other thing I want to point out to you is, and why CSO data is valuable, is that it samples other areas of the landscape that SNOTEL sites wouldn't hit. So in the upper left here, this is basically just a distribution. Think of it as a histogram. It's a distribution of the elevation of SNOTEL sites. That's what you see in the cyan color. And then CSO observations. That's what you see in the dark blue. And the dark blue is over to the right, okay? So CSO observers go to higher elevation locations than SNOTEL sites. And then if you look at the figure in the upper right, this is the same sort of idea, but it's for slope angle. Okay, remember I said SNOTEL sites tend to be in gentle meadows, nice, easy elevation areas. And that's why the histogram, the cyan histogram in that upper right figure is way over to the left. Okay, these are low angle areas. Look at the blue line, the dark blue line. These are our CSO observations. So our CSO people are skiers, snowmobilers, snowshoers. They're people who are out in this more complex terrain on steep slopes. So they're going places where we don't currently have information. So just a few words about participation. You know, since starting in 2017, the CSO project has grown very steadily. We've had in excess of 30,000 observations from more than 4,000 unique observers. And participation is heavily concentrated in North America, but we do have global reach, okay, and around the world, which we actually think is really pretty cool and pretty impressive. Okay, so that's kind of what the CSO project is in terms of, you know, how it works, who's participating, but the question is now, does any of this really matter? You know, where's the value added? Will these observations actually improve our ability to model high mountain snowpack? We tested this by doing 4 sets of runs, right? And that's in the different colors there. We did tests where we don't assimilate any data. We do tests where we assimilate in just CSO data. We do tests where we assimilate just SNOTEL data. And then we do tests where we assimilate both. And we kind of like look and we see what's the model performance in each of these categories. So I have a million model results, but I'm going to just basically show a single slide here to keep the story simple. Okay, so this plot is showing you the modeled snow water equivalent to the as a function of the day of year. Okay, the y-axis has SWE on it, the horizontal axis is day of year, and basically what we see is the black line. These are the observations. This is what the SNOTEL station sees, right? So that's ground truth. That's reality. The sort of the blue line, the highest one that you see there, this is basically the best job that we can do. We've calibrated our model, we've made it as good as we can, but we have not assimilated in any data. And as you can see, our model is predicting too much snow, and the snow sticks around for too long, right? When you look, when that goes back down to 0, it's about a week to the right, okay, of the actual observation. The third line that you see, okay, this kind of greenish line, that's what we get when we assimilate in CSO observations and snow telemetry data. And you can see that it's almost spot on. So it's really, really good. And so we've done, like I said, we did tests with just CSO, just SNOTEL, both. What have we found? Well, what we have found is that when we assimilate in CSO data, we absolutely get a big improvement over our regular calibrated model. When we assimilate in just SNOTEL, we get really good improvement. When we assimilate in both, we get even better improvement. So in every case, there's value added by having these CSO observations assimilated into the modeling that we do. Okay, so that kind of brings me to like the third part of what I wanted to talk about was like, okay, this is all great modeling that, you know, my students and I do in our office, but how do we return this information to the public? The public are the ones that are giving us this high value data, and it was important for us to return this data. Okay, so MountainSnow.org is a website that we launched last summer, and basically we do near real-time modeling the snowpack. You know, participants have asked us for this. They've wanted to know how much snow is out there, and this is how we return it to them. Okay, so my final portion of my talk is just kind of a quick tour through this. I will note that MountainSnow.org is really optimized for desktop. We don't have this working great for a mobile application, but we're still working on that. Okay, regardless, this is what you see when you basically go to check out the app. This is the homepage for MountainSnow.org. You can see all of our modeling domains in the red boxes there. Our New Hampshire domain is the singular one out east. There are links at the upper right, which you should absolutely visit because they will sort of take you through an introduction. They will give you a brief tutorial. They will explain how to use the website and what's being displayed at this website. We add new domains to this on a rolling basis, and we do this basically in areas or pockets where we see significant CSO activity. So we are responsive to the community in that sense. The other thing is that everything that we do is super highly automated, right? We want to be able to just like, you know, snap our fingers and pop a new modeling domain under this website. And we do this by kind of automating all of the scripting that we do. We fetch weather data in an automatic way. We do the quality assurance in an automatic way. And this makes it easy to scale up our project. We use Snowtail data. We use scan network for calibration. That is the one limitation of kind of where we can set up new domains. So in the sort of center part of the country where there are no scan stations or Snowtail stations, that becomes a little bit more of a challenge. Okay. So this image here, I've kind of just sort of zoomed in on both the Western United States and our one domain here in New Hampshire. This tries to highlight to you how we build out modeling domains in areas with the high concentration of measurement. So all of the points, all of the sort of purple dots that you see, these are CSO observations. And so we kind of go in and drop boxes on these little clusters that we see because there's a lot of backcountry users out in those areas. There definitely are still some areas we don't have quite covered, sort of kind of upper sort of northwestern Montana and also northern Idaho, and then also the Uinta Mountains kind of near Salt Lake City. We're getting to those, but we're doing all right. Okay, so for kind of a quick tour, I just kind of want to introduce you to some of the functionality. So this is an app which was created using Google Earth Engine, and so it'll feel comfortable in some ways there. As with all things Google, right? You can choose like a map view or a satellite view or a terrain view, and it's kind of personal preference. I like terrain because I like to sort of see the mountains. And then also, if you come up here and sort of hover over this layers box, which is in this red circle, it'll allow you to adjust the transparency of anything, which is nice because you might want to make a snowpack that is being overlaid on top of the terrain. You might want to make it transparent so you can kind of see the individual mountain ridges underneath. The next thing is that we have a date slider here, which allows you to sort of go back in time. Right, we started archiving these model results on October 1st of 2020, so we have about 2 years of data stored online that people can go back and explore. And presently, it comes up to I think 3 days before today, so we have a little bit of a lag there that we're working to close to make sure that this is fully real time. A couple of other things that we've done with this website is that we don't want this to be just all about CSO. We actually built into this website the ability for anybody using it to learn about other sources of snow information. So for example, you can turn on the CSO results. And so this is a particular day for the New Hampshire domain, or you can turn that off and you can turn on the SNODAS model. And I think that this is really useful because you can kind of appreciate how much of a difference there is between a coarse model like SNODAS and then a fine scale model like CSO, in terms of being able to capture the distribution in really highly variable terrain. Just a couple of other things to note. We also have in here the ability to just play around with the visual aspects of what you see. And so we have sliders in there that are going to kind of allow you to sort of set the color bar range for snow depth, snow water equivalent. And so here I sort of picked two extremes, right? And you can kind of tell both of these are fairly unhelpful. The picture on the previous slide is kind of the best view here in terms of being able to see what's going on with the snow. But this gives the user some ability to sort of set it up the way that they think it looks the best. Okay, so there are some controls like that that you can use. A couple of other things that we've added sort of just more recently, you can kind of click on and extract data at any point of interest. And we did this because we were hearing from like a lot of educational programs, like, hey, we went out to this particular ravine, last week, and we made some measurements, and, can you tell us what your model says the snow depth is at that location? And so, you can certainly get it from the colored information, but it's nice to be able to go in and just click on an exact spot, and it'll spit out information about what the snow depth is estimated to be there. Something else that we've done to sort of help people better visualize snow extent or snow covered area is that we've added to the MountainSnoworg website various satellite products that will allow people to just sort of compare many different things. Okay, so for example, we have this thing set up so that it'll display sentinel imagery, which is quite nice. and that has a resolution of about 50 meters. And so the picture that you're seeing, I didn't write down the day of the year. This is from sometime maybe like last February or so. This is a picture of our New Hampshire domain, and you can see the great satellite image of the snow cover. The thing that you're seeing in the middle, this is what's called the MODIS reflectance. Okay, so the red sort of marks there are coming from the MODIS sensor on the Terra and the Aqua satellite. And you have to think of this as kind of a binary mask. It's kind of a, is there snow or is there not snow? So wherever it's colored red in this case, this is where the MODIS satellite is basically saying, yes, there is definitely snow. And you can see there are some big differences here. So this is really important. These satellite products are fantastic, but they have a lot of differences. You know, because you'd look at this and you'd be like, okay, on this particular day, MODIS is completely underestimating the snow cover, which I would agree, it is. So it's nice to allow people to kind of compare these things. And then finally, at the lower right, I've just simply turned on the modeled estimate of snow distribution from the CSO project for this particular day. And you can see that it agrees very much with the Sentinel imagery of having broad coverage of snow across the entire domain. A couple other things. You can turn on a 72-hour snowfall layer. So this still image that you're looking at in the left side of this picture, this is from February 5th of 2022, and it shows the significant storm that occurred at the start of the month. This could be super useful in terms of identifying heavily loaded slopes, right? So to be thinking about avalanche hazards. Now there's a couple of things here. The plot that I've put in at the upper right of this slide, this is the scan site at the Muskoma River, okay, which is pretty far southwest of our modeling domain. But I'm showing it to you because you can see that, and I realize it's kind of small and hard to see, but the vertical axis is snow depth, and the horizontal axis is all of February. And so you see the big jump up that occurs in the snow depth. That is exactly what the CSO result is showing you at the lower left, okay? Now, the plot at the lower right, which looks really strange, this is the scan site at Hubbard Brook, which actually is in our domain, down at the lower left corner of it. And you can tell something's not quite right there. So that the scan site at Hubbard Brook shows about a 5-foot gain in snow depth, okay, at that particular day. And then you can see there's another one of these 5-foot increases in snow depth that occurs late in February as well. That's a bit of a problem in terms of the things that we do, and we find that this is kind of a challenge with these scan sites that exist in the eastern US. We get a lot of anomalous data like this, which makes it really hard for us to pull this data into what we do. On top of that, some of these scan sites also measure snow water equivalent, and we've had a lot of problems with those data as well in terms of data quality. So for example, like we'll get a lot of negative values for snow water equivalent, which is impossible. It has to be a positive number. Okay, but I just kind of wanted to point out to you the fact that the model result here does agree with the snow increase seen at the scan site in the upper right, but the scan site in the lower right is clearly something's gone wrong. And then this is just later in the month, so I'm just showing you here again. I'm showing you 72-hour changes in snowfall. This is coming in sort of late March. Actually, this is late March 2021. It is. And basically, we have very, very rapid snowpack retreat. And you can see that when you animate these pictures, too. It's really cool. It's like this movie of the snowpack disappearing. So that's quite nice. Okay, finally, users can see the direct impact that their measurements are making. And we show this by subtracting results that come from runs with assimilation and runs without assimilation. However, this is presently not an option that we have available for our New Hampshire domain. And this is due to what I was just trying to talk about. This is due to the lack of consistent, reliable, and real-time data from the scan stations that we have on the East Coast. I will point out that with regular CSO domain data coming to us in the domain, we can use that CSO data to run assimilative models in New Hampshire, but we just need that data to be kind of coming in on a semi-regular basis. But for right now, what we're doing for New Hampshire is not assimilating in data. So that's kind of my challenge I'm throwing out to your entire audience, is to really build up a community that is regularly submitting these data to us. Having said that, I do want you to see what this looks like. So this slide that you're seeing here is an example from this past April in Colorado. And the different colors, what it means is like where it's dark blue, it's showing you that through the act of people participating in the program, it is deepening the snowpack. So it's fixing the snowpack in the positive direction. And then in areas where it's red, what that means is, again, through community participation in this project, it's shallowing up the snowpack. So it's kind of fixing the snowpack in the negative direction. Okay. So these model corrections are really critical, and public participation in CSO has an immediate impact on improving snowpack simulations, and it's one that we can show to people so they can see that they are having a direct difference. Okay, so I'm going to wrap it up here. Let me bring it back to the initial idea behind this project. Right, our science team, we saw an opportunity. There is definitely already a lot of snow information out there for scientists and also for the general public to use and consume in whatever way they want. However, there are plenty of gaps in what we know and in what we can observe. So having the public help us to fill those gaps is really the core idea of what CSO is. That said, a lot of times what are called community science projects or citizen science projects, they sort of fall into this one-way path of participation where the participants really turn out to be just data collectors for the science team. And from the beginning, we wanted to listen to, we wanted to be responsive to our participants, and we wanted to return to them information that they had asked for in the locations where they have asked for it. And that's really what MountainSnow.org is all about. Their participation makes that information much more useful to everyone and much more accurate as well. And the icing on the cake is really that participants frequently report back to us that by participating in CSO, they let us know that they have really learned a lot of new things about snow, about how it changes, and about why it's important to their everyday lives. And so to us, that's really high praise. And so we are thrilled to hear those sorts of things. And it's the best kind of win-win, and it's really what kind of keeps us motivated to keep doing what we're doing. So as I close, I just want to mention one last thing. So MountainSnow.org is really a public-facing website. We created it to be fairly easy to use and understand with those tutorials and introductory material at the links up right. But we do also hear from people who are science-oriented, and they're like, hey, we would love to actually, get our hands on your data and use your data. And we are very big proponents of open science and transparency. And so everything that we do in terms of the data that we collect, the model data that we produce, it's all freely available. And so I'm very happy to at any time point people to those kinds of things. So that really wraps up my presentation. So I just say thanks again for coming to this great meeting. I'm planning on sticking around and hearing the rest of the talks as well. And I hope you have a fantastic start to your snow season.